So our next talk will be by Oreoluwa Alao, who will be presenting on modeling chaotic spatiotemporal systems with echo state network.
Thank you for the introduction. So I'll be speaking to you guys today about my research into a new method for modeling chaotic behavior in physical systems. Now, the analysis of physical systems, in which understanding both the arrangement in space and how this changes with time, is ubiquitous in physics research, especially in the fields of fluid dynamics and computational plasma physics. Yet, despite recent advancements in our theoretical and analytical methods for modeling these systems, and even our data-driven machine learning approaches for modeling these systems, our ability to predict the behavior of these systems is significantly limited when these systems exhibit what is known as chaotic behavior. In a chaotic system, slight differences in starting conditions result in drastically different outputs. And this can be easily visualized with the classic double pendulum example. These two pendulums were dropped from approximately the same starting point, but you can see that as time progresses, their trajectories quickly diverge into chaos. And this is a similar issue when you're trying to model chaotic systems. When you're off by even 0.01% in your model, your model is going to be rendered obsolete within a short amount of time. Now, recent research has shown that a new machine learning approach known as reservoir computing has an unusual ability to outperform other machine learning approaches when modeling chaotic systems. This is the graph showing the propagation of a laminar flame front in time. And when you subtract the model's prediction from this graph, you can see that the model is able to match the actual system 1-to-1 up until 8 Lyapunov times. In other words, 8 units of time before the system diverges into chaos. Now, how is reservoir computing able to outperform other machine learning methods? Well, it's in its approach. It doesn't try to learn the dynamics of the system. Rather, the reservoir computing approach is that you have the model inherently have the dynamics of the system. And this can be easily visualized with a fictional example. So let's say the propagation of seismic waves in a solar quake is exactly the same dynamics as the ripples in a pool of water. Then it's quite easy to model this system. You just get a rock and drop it in the pool of water. And then you find a way to correlate the behaviors of the ripples to the system that you're trying to model. Now, this modeling approach seems quite trivial, but it becomes valuable when you're trying to model something such as a chaotic system where traditional modeling approaches apply. And this is the approach taken on by a neural network known as an echo state network when trying to model systems. So the echo state network is similar to a recurrent neural network in that it keeps a record of time and thus is able to determine time-related dependencies in your system. The main difference, however, is that the majority of the network's perceptrons are randomly initialized and fixed that way. And the only trained portion of the network is the output layer. Since the network's perceptrons are randomly initialized, then there is no pattern in the way that the perceptrons are connected. So input data is scattered, even if they're slightly different, they're scattered in completely different areas inside the high dimensional space of the reservoir, kind of emulating how slightly different initial conditions result in drastically different outcomes in a chaotic system. And this effectively emulates chaos. It's the job of the readout layer to translate these chaotic behaviors in your echo state network to the system that you're trying to model. So we can see how this approach is able to achieve complex dynamics with a significant fraction of the computational cost, since you're only training one layer. Now, the disadvantage to this approach, however, is that it is not readily applicable to experimental research. And this is because when you're creating models in experimental research, you need both predictive ability and interpretability. The echo state network is not interpretable and functions much like a black box. This issue can be resolved, however, if we can integrate the echo state network with an architecture that is already known for its interpretable predictions, the variational autoencoder. And the specific autoencoder that we work with is one developed by my mentor that is able to take in spatiotemporal data from an uncontrolled experiment and extract the key variables that define those dynamics. It is then able to base its predictions off of these key variables. Now, the fact that the predictions are based off of values that are interpretable to humans makes the prediction interpretable. So you can see that if we can integrate the echo state network with the variational autoencoder, we will have enhanced predictive ability and interpretability. And this is where the goal of my research lies. Now, there are 3 steps that need to be taken to make this a reality. First, we need to develop an echo state network that is compatible with the variational autoencoder. Then we need to evaluate its performance independently to make sure modifications do not detract from its predictive performance. finally, we need to test the integrated architecture as a whole. And our research takes the first 2 steps to achieving this goal. Now, when designing an echo-state network, you first have to start by looking at your system and designing a reservoir that has the same internal dynamics as your system. We chose the Kuramoto-Shchivinsky equation because it is a well-known chaotic partial differential equation that models laminar flame fronts. And we got our reservoir to match the dynamics of the system by looking at the Lyapunov exponent, which is a quantification of the chaos in the system. We then enhanced our model's prediction performance by enabling it to process the data in a hierarchical fashion. So instead of using a single reservoir, we stacked multiple reservoirs on top of each other, where each reservoir layer processes your input data at a different level of abstraction. So at the highest level of abstraction, you'll be looking at in what direction is your data flowing, or where do the branches begin? And at lower levels of abstraction, you look at where the tiny branches begin to appear and how the data evolves from time step to time step. Finally, we gave our model a spatial inductive bias by making it behave like a convolutional neural network. In other words, it only processes a small window of the input data at a time, forcing it to take into consideration how local interactions affect the development of your system. So once we developed this custom echo-state network architecture, our next task, and arguably the most difficult, was finding a way to make it integratable with the variational autoencoder. And this is done by considering how it is trained. The echo-state network, since you're only training a single layer, is able to be trained using a simple approach known as linear regression. However, when you connect the echo-state network with another architecture, you're training more than one layer, and linear regression is no longer applicable. And thus, you no longer have the clean and precise solution that linear regression applies. You have to rely on the traditionally used gradient descent method when you're training a variational autoencoder. And this is more error prone, and you'll see these in the results in the next few slides. So we tested our data on 1,000 simulations of the Kuramoto-Shchivinsky equation. And to try and resolve the limitations that the gradient descent method proposed, we tested different training approaches and evaluated how they affected our model's predictions. So our first training approach was by letting the model base each prediction off of its own previous output. And you could see that the model is able to make accurate predictions up until a certain point. I highlighted the most distinct sections for you. But after this point, the model quits its predictions. It realizes that past the point that it is very confident, since it is unable to determine the exact system state, it might as well stop predicting just to cut down error. Now, comparing this result to, and this can also be seen in the error graph. If you look at the graph of error, based on how long the model is predicting, it just suddenly cuts off its predictions. Now, the error is very similar to that which was achieved with the variational autoencoder when it was trained normally. However, we need to figure out a way to solve this confidence issue where the model just stops predicting. So we tried to emulate a similar training approach that is done when you do linear regression, which is allowing the model to see all the system data. So this approach we split up in 2 different ways: teacher forcing and scheduled sampling. In other words, allowing the model to peek at actual system data at different times before making its prediction. However, this resulted in the model only considering short-term dependencies. And this can be visualized in this example by seeing how the model only predicts a linear translation of previous time steps, because that's what the system looks like on a small scale. And when we reduce the amount of times the model is able to peek at actual system data, it only makes patchy predictions, largely correlating to the places where it wasn't allowed to peek. So these approaches where we give the model actual system data was not optimal in the gradient descent approach. So then we decided to interpret this confidence issue in a different way. Well, the model's facing confidence issues because it's wrong too often during training. So we decided to train it on non-chaotic data where it's more likely to be correct, and then test it on the chaotic data to see if its confidence improves. And it does. If this is the model, if this is the actual system, you can see that the model prediction carries through the entire time. Now, the error is not as good as when we had it train on chaotic data, which you could see when looking at the different error graphs, just how significantly higher this training approach's error was. But the results are more physically accurate in that it carries out to the end. Now, due to the limitations of due to time constraints, this is where our research had to end. But we were able to learn valuable lessons when trying to move forward with making ecostate networks applicable to research. We developed and proposed a deep convolutional ecostate network, which is capable of making predictions on spatiotemporal systems. So we were able to correctly identify the structural components necessary for this task. And then through our testing, we were able to narrow down what our training approach should be to be able to be successful in creating an integratable ecostate network. We need to combine autonomous prediction, where the network is only basing its predictions off of its own internal data. And then we need to practice training it on non-chaotic regimes. In other words, training at least somewhat of the way on non-chaotic data so that it learns to have the confidence to predict all the way. And then finally, we need further optimization before we can integrate our network with the variational autoencoder. So for future work, we definitely need to investigate gradient descent training approaches for ecostate network. In past literature, this has not been done because linear regression was all that was needed, since the ecostate network was only tested independently. But now that we're trying to make the ecostate network applicable and interpretable, we need to leave these traditional training approaches behind and investigate new ways of working with the architecture. So with more development, we'd be able to benefit from it in the research field. And then below, I also listed some other areas that would help us to fine-tune our models' predictions, looking into the internal dynamics of each of the reservoirs and making sure that this way that we stack the reservoirs doesn't affect the way that they need to be initialized. Then we also need to look at possible ways of automating the approaches for initializing the ecostate network, which will make it more easily generalizable. And then we need to test the ecostate network in conjunction with the variational autoencoder. I'm working on this project, and I would love to thank my mentor, Mr. Peter Liu, and Professor Marin Soljačić for giving me the opportunity to work on this research. I'd also like to thank Dr. Rickert for his constructive feedback and support, the TAs, Albert Wang, Shloka Janapati, Emma Zabarsky, and Amula Peluta for their help in reviewing my paper. I'd like to thank RSI, CE, and MIT for organizing this opportunity, the United States Department of Defense for their sponsorship, and all the people who sponsored my RSI experience. I'm very grateful for that. And I'd be happy to take any questions.
Thank you so much, Ori, for the great presentation. Now, if any of the judges have any questions, please feel free to ask.
Yeah, so you saw qualitatively by looking at the data that there are times when the predictor was losing confidence.
Mm-hmm.
Do you think you might be able to detect that in an automated fashion? Because sometimes, although having a prediction is good, knowing that it actually is a worthwhile prediction is better.
Yeah. So you can quantify the quality of predictions by plotting the mean squared error of the model's predictions with respect to time. And this is what we did do to get a quantitative estimation of how well the model was doing. And for typically errors of around around 1 and below were most accurate, while higher than that, the model would diverge into inaccuracies.
Right, so that's not quite what I'm asking about. So what I'm asking is, if all you have is the prediction, you don't actually have the actual data to compare it to.
Mm-hmm.
It still looked qualitatively like you were losing confidence. So there are some parts of the prediction that your model was more confident of than others. And that's what I was wondering whether you could detect, because that would be useful information over and above what the prediction is, knowing, okay, you should ignore this part of the prediction because the model doesn't think it's worth anything.
So is your question asking if we can use this model tendencies to only predict where it's confident to quantify what the quality of a prediction is?
Exactly, because I imagine some initial data is going to be easier to predict from than others in a real system. And so if you can tell, okay, this one, the model's able to predict out a couple of time steps as opposed to the usual 8 time steps or whatever, you know, that would be useful because it's telling you something about, you know, okay, maybe this initial data is actually harder to predict from.
And thank you for your question.
You don't, yeah.
That is definitely an interesting way of utilizing this unusual tendency of the ecostate network when it is trained with gradient descent. And it is one that I would definitely have loved to test, and one that I considered However, due to time constraints, we weren't able to test how we can utilize this, this confidence tendency to evaluate how worthwhile the model's predictions are. But that is definitely an area worth researching.
Okay, thank you.
Thanks for your interesting talk. I was wondering, I know you focused on prediction of actual space-time trajectories, but did you explore whether the network can model more global features of the chaotic dynamics? That is, can it estimate the Lyapunov exponents or the metric entity with any accuracy?
Yes, so previous research has shown that you can use echo state networks to estimate the Lyapunov exponent. And the way that the Lyapunov exponent is estimated is by seeing how slight perturbations in your input data, how quickly that causes the model to diverge from the actual system. And that has been successfully demonstrated with echo state networks. If that is your question.
Yes, thanks. And one more question, if I may. Can you tell us a little bit about how the complexity scales, that is, for a given number of spatial grid points, or maybe space-time points, how many nodes do you have to put into your reservoir to get good behavior?
So it's with our specific reservoir architecture, we didn't want to face this problem where we had to try multiple different reservoir size scalings just because we were increasing the size of our network. So this is part of the reason why we were motivated to employ a convolution, using the reservoirs in a convolutional approach, where we, each reservoir was responsible for processing only a small portion of the data at one time. And then we were able to piece these individual predictions together to get a global prediction. And this way you can definitely keep down your memory size because you're not linearly scaling the size of your reservoir to fit your problem. But yeah, typically if you're only using a single reservoir, you would have to scale it proportionally to the size of the system that you're trying to model.
So how many reservoir nodes in all did you use for the problem? How many spatial grid points were in your simulation?
So each stacked reservoir had 5,000 perceptrons, and the results showed on this page was achieved by using just a single reservoir.
How many grid points were used in this simulation?
So this was 150 by 150, or 150 by 256. That's what it was trained on, but I cropped the window size for easier fit on the slide. So it trained on a mesh of 256 by 256. Yes, yes.
Thank you.
Hi. I think this is all really interesting to predict chaos is just amazing, right? That we can do anything. I was wondering, how does this prediction, and I love your graphics because it sort of makes it easy for someone outside the field to I don't even know if it's literally data, but it clearly shows, right, that it's doing prediction and you can see the lines. So I'm completely outside this field. I'm wondering, how does it compare to just literally a random forecast? Does it really perform better than random, and how do we know?
So we know that it performs better than a random forecast because, well, partially because of previously reported reports that said that the echo state network is capable of predicting to 8 Lyapunov times. This has not been achieved, been able to be achieved with traditional neural network approaches, such as LSTMs or GRUs, which are other recurrent neural networks, where the entire architecture is trained. But by only training the output layer, and by causing the reservoir to have the same dynamics as the system that you're trying to model, you're able to get further in your predictions than more complex approaches, which can kind of seem counterintuitive. But in the example that I gave with the seismic, the solar quake and the ripples of water, you can kind of see how or what intuitively why this approach might be better. Now for randomly initialized reservoirs, this is not feasible because for your reservoir to work, it has to have what is known as the echo state property, which is a tendency to decay the effect of previous time steps as you continue to progress to make predictions. That is one way that you can summarize it. So there is kind of a method to the madness of randomly initializing your reservoir. But it's for these reasons, achieving the same chaotic dynamics in your reservoir, having this echo state property that enables this to perform better than a randomly initialized recurrent neural network. I hope that answered your question, and thank you for asking.
All right, thank you so much, Ori.
Thank you.